In the previous section, we computed Ez, the intensity of the electric field caused by the charged plate at the distance z from the plate. And the result was surprisingly independent of z. That means the intensity is constant, independent of the position. Actually, this resembles the situation of a gravitational field in this room. Gravitational field is constant, goes down, and it is independent of the position. And then the potential is proportional to the height. Potential, right. Fine. Another approach is not to integrate to compute the intensity, but we can integrate to compute the potential. This has sometimes the advantage that intensity is a vector, and we must consider the direction of different contributions. This was here when we considered that this vector has only the important component in the vertical direction, because its component in the horizontal direction will be cancelled with another vector from this source. If we consider potential, this is a scalar function, and we don't have to consider any direction, we can just add all the contributions of all these pieces in the plane. So let's compute the same result, potential and intensity, using phi. So once again, here's the plate, here's the point in distance z, and we want to compute phi. So, for one charge, Q1, the phi is given by this formula, 1 over 4 pi epsilon with minus, and Q, the charge, is the charge density sigma times dx dy, the element of the surface, divided by the distance r. This is r, this is rho, so r is 4 pi epsilon sigma, and r is square root of z squared plus rho squared, and rho squared is x squared plus y squared plus z squared dx dy. Yeah, sorry, and we integrate over the entire plane. R2, because we have two variables, x and y. We can again transform to polar coordinates. Yeah, we can factor out, okay, minus 1 over 4 pi epsilon sigma over square root of, and x squared plus y squared is rho squared. Yeah, rho squared plus z squared. And instead of dx dy, we have rho d phi d rho. Rho goes from 0 to infinity, and phi from 0. Phi is the potential, sorry, let's call it alpha. And alpha goes from 0 to 2 pi. So we have minus sigma over 4 pi epsilon. We can factor out over alpha. we can integrate over alpha, which gives 2 pi, and just the integral from 0 to infinity remains, and we have rho divided by square root of rho square plus z square d rho. But unfortunately, this integral does not converge. If rho is very large, you can forget z, and you have rho divided by rho, which is 1. An integral of 1 from 0 to infinity is not a finite value. This integral does not converge. It is equal to infinity. If we use substitution, then we can use substitution. Rho square plus z square is u, then 2 rho d rho is du, and then we have minus sigma over 2 epsilon integral. When rho is 0, u is z square, and when rho is infinity, this is infinity. 2 rho d rho, so 1/2 of square root of yeah, 1 over square root of u du. And yeah, if we write the 1/2 here, then the antiderivative is square root of u from z squared to infinity, which is infinity. Too bad. So, in this way, we cannot find a potential as a function of z, but if we are interested in the voltage, in the change of potential alone, then we could find phi z minus phi 0, and that would be the potential, that would be the voltage, the difference in potential at the point z minus the potential at point 0, and this gives a finite value. It is a similar expression as here, but we must subtract this expression at z is 0. So we can go up to here. We can go even up to here, and we have minus sigma divided by 2 epsilon integral from 0 to infinity, and phi z gives this rho divided by square root of rho squared plus z squared minus the same when z is 0. That means minus rho divided by square root of rho squared plus 0 squared, if we write it very slowly. And then this turns out to be finite. Okay, let's compute this. If we evaluate the integral, just the indefinite integral alone, then we can use again substitution. So let me write it once again. Rho divided by square root of rho squared plus z squared minus, and if rho is positive, this is equal to 1. And once again, rho square plus z square is u, then 2 rho d rho is du, and we have indefinite integral rho d rho, so we have 1/2 2 rho d rho, which is du, divided by square root of u minus minus integral of 1 d rho, which is rho. And integral of 1/2 square root of u is square root of u minus rho, and u is rho square plus z square. And we want to evaluate the limit of this for infinity, for 0, and subtract. The limit at infinity is 0, which can be computed this way. Limit for rho going to infinity, square root of rho square plus z square minus rho. If we divide and multiply by sum, rho square plus z square minus rho, and we multiply by square root of rho square plus z square plus rho, divided by square root of rho square plus z square plus rho, and limit for rho approaching infinity. Then you know the formula: a square a minus b times a plus b is a square minus b square. So this is limit for rho going to infinity. Square of that minus square of that, which is z square, divided by rho square plus z square plus rho. And when rho goes to infinity, the denominator goes to infinity, so this limit is equal to 0. So this is the antiderivative of this bracket. So we have minus sigma divided by 2 epsilon, and the antiderivative is square root of rho square plus z square minus rho from 0 to infinity. At infinity it is 0, and at 0 it is z. So the result is sigma z divided by 2 epsilon, which is in perfect agreement with the intensity, because if we integrate this constant along z, we get sigma z divided by 2 epsilon. Well, and the rest is the same. So you see, this was an application of a double integral, where we can integrate either E or the intensity of the electric field, or we can integrate potential. There was a little problem that if we consider potential at some point z, then the result is 0, infinity. And when we consider only the difference of potentials, the voltage, then it turns out to be finite. And you see, the change of the potential is proportional to z. That means the gradient of this is a constant function, the intensity of the vector field. And as I said, this is similar to the gravitational field in this rule.